Hi everybody, it's me. This lecture we're going to start with section 4.1 and we're going to finish up with section 4.3. The 4.1 and 4.2 have a lot of definitions and just kind of some concepts that are worth a read over in your textbook. So I'm going to kind of gloss over those so I can spend some more time doing some calculations that are in 4.3. So the first little bit of 4.1 talks about the first part of 4.1 talks about just how water is essential for us. So just a couple of points. It's essential for a lot of reactions that keep us alive. Water is H2O, is essential for life. It moderates the Earth's temperature. It cools engines, cools nuclear power plants. It's involved in a lot of industries. And we use it a lot for transportation, so just in our daily life. In chemistry, water is especially important to us because it is able to dissolve many substances. Okay, it's able to dissolve many substances. So the reason for that is because of the structure of water. So on the screen is a Lewis structure for water, and some of the things that are important to note are that this molecule is a bent or V-shaped structure. And so what that means to chemists is that there's an approximate bond angle between these of 105 degrees. And so we are sharing electrons within our covalent bond, but oxygen has a greater attraction for the electrons. So that gives it what's called a dipole. Oxygen attracts electrons, a term that we're going to come across later in the year. It's called electronegativity. Sorry, I ran out of room. So oxygen has a higher electronegativity, and so that's going to give this molecule an overall partially negative charge. So this is going to have the partial positive charge. Okay, so this V shape of the molecule and the fact that there's an unequal charge distribution makes water polar. So a polar molecule is an unequal charge distribution. So there's part of the molecule that is already more negative. Okay, this is what gives water the ability to dissolve. Ability to dissolve compounds. Okay, so hydration is a process that we're going to talk a lot about in this chapter. So here is hydration. When we have a salt that breaks apart in water, they're going to break apart into their individual cations and anions. Okay, so this solid notation, it's just like when you're dissolving like saltwater solution. It starts out as a solid, but because of the nature of the cations and anions, it's able to break apart into its ions when it's in solution. Okay, so anytime you see the symbol AQ, aqueous, that means that it's going to exist as ions. Okay, and so we're going to use solubility rules to determine, is this compound going to be able to break apart? So I gave you solubility rules in class, and that's how we're going to determine whether or not a solid is going to break apart. Okay, so whenever you hear the word solubility, that means the ability to be dissolved in water. Okay, So if you hear something is soluble, that means it can be dissolved. If something is insoluble, it's not going to dissolve. It's going to stay as a solid. Okay. So another word for soluble, that means that we're going to have what's called dissociation. Okay. So dissociation is what's represented by this equation that's on the slide, taking something that's in a compound and dissociating it into its ion pieces. Okay, so water is especially important to us, and the fact that it can dissolve things because it's polar. Okay, so because it's polar, it's going to be able to dissolve. Polar dissolves polar. Okay, water is polar. And it's also going to be able to dissolve ionic compounds, because ionic compounds are going to have an ability to have that unequal charge distribution like water does. So it's going to be able to get picked apart. Okay. Okay, so polar can dissolve polar molecules. Water can also dissolve ionic molecules. But we're also going to talk about how it can also dissolve. So something being polar is referring to it being covalent. Okay, so one example that your textbook gives is ethanol. Okay, due to the structure of ethanol, it's going to have this oxygen in it that's electronegative, and so we're going to have a more positive side and a more negative side, just like the water molecule itself. Okay, so a general rule for solubility, to predict solubility when you're dissolving one substance in another, is going to be like dissolves like. In my classroom, I have a pretty funny, well, I think it's funny, a pretty funny meme about a polar bear thinking that he's dissolving in water. So poor guy doesn't know chemistry very well. All right, so moving on to section 4.2, it's time for us to start talking about solutions. Okay, so in chapter 1, we talked about mixtures. You guys separated some mixtures. Now we're going to talk about a more specific mixture, a solution. Okay, a solution is a homogeneous mixture, so it looks the same throughout. Okay, we cannot see the individual pieces. We put a solid in, we dissolve it, and we can no longer see the solid anymore. So we change the composition by changing the amount of the dissolved substance. So these are two vocabulary words to know: solute and solvent. Solute is what's being dissolved. The solvent is the dissolving medium. This is most typically good old H2O. When you make a solution in my classroom, you are going to be dissolving it in water. Okay, so some solutions are called electrolytes. Okay, an electrolyte is going to be able to conduct electricity. So over here on my picture, this is a strong electrolyte versus a non-electrolyte, and in the middle we have a weak electrolyte. Okay, so the strong and weak electrolytes are determined by the solute. Okay, so electrolyte property depends on the solute. Okay, what is being dissolved. So there are strong electrolytes, which obviously conduct a current very efficiently. Weak electrolytes have a small current. Non-electrolytes do not permit a current whatsoever. Okay, so strong electrolytes are going to be salts, which are ionic compounds. So when you break apart an ionic compound, you get a positive and a negative charge. Think about your car battery. Okay, they're also going to be strong acids and strong bases. Okay, so not every acid is a strong acid. Not every base is a strong base. Okay, so both of these lists that I'm going to put on the slide over here, you've got to memorize. Okay, so a strong acid: hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, chloric acid, perchloric acid, and sulfuric acid. Okay, so these acids are always going to completely dissociate. They are going to completely break apart. Okay, so I have a positive ion and a negative ion. Okay, the list for strong bases: lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide. Notice that all of those are in group 1. That's going to follow a trend for your solubility rules. Okay, these strong bases are also going to completely dissociate. So calcium hydroxide, strontium hydroxide, and barium hydroxide. So these two lists are worth committing to memory. 1, because they're going to matter when we start doing stuff with solubility rules. 2, I think I try to sprinkle in a multiple choice question on your test that just asks you to identify which is a strong acid, which is a strong base. So strong electrolytes completely dissociate. And remember, we talked about what dissociating means back in section 4.1. Okay, so strong electrolytes conduct current very efficiently, or they completely dissociate. They completely break apart. Okay, weak electrolytes are going to break apart a little bit. So acetic acid, the formula is HC2H3O2. So this will break apart into H ions and C2H3O2 ions, but some of the compounds are just going to stay together in solution. Okay, non-electrolytes don't have any current whatsoever, so I'm going to have no positive and negative charges in a non-electrolyte. Another good example for a non-electrolyte is ethanol. Okay, it's not going to break apart. I'm not going to have any positive or negative ends, so it's not going to conduct any electricity. Okay. All right, so this leads us to molarity. Okay, molarity is one of the most important concepts in this chapter. We're going to work some word problems like you guys saw in Chem 1, but we're also going to continually revisit this basic definition, not just here in chapter 4, but as we move forward into gases or if we're working with thermodynamics. So molarity is one of the most important concepts that you can take away from me. Okay, so molarity, big capital M, is the moles of solute per liter of solution, always. Okay, anytime you see a big capital M, you can think about the units of moles per liter. Okay, we use this basic definition over and over and over again. So the first problem that we can work is one like you would see in Chem 1. Calculate the molarity of a solution in which 186.4 milligram sample is dissolved in enough water to make 500 milliliters of solution. Okay, so in this problem, we want to find M. This is what we want. So we need moles of the solute over the liters of your solution. Okay, they gave us milligrams and they gave us milliliters. So we've got a couple of conversions to make. So pause me, make the simple conversions, and then unpause me. All right, so if you've unpaused me, I hope that you've worked your problems just like I have written here. Milligram to gram, gram to mole, and then just milliliters to liters. So now to calculate our molarity, I'm just going to take the moles, oh no, I forgot my exponents. Hold on. There we go. Sorry, I forgot my times 10. So 6.275 times 10 to the negative 4 moles divided by my liters, 0.5000 liters. Both values have 4 sig figs. And so that gives me 0.001255 molar. If you wanted to put this in scientific notation, 1.255 times 10 to the negative third molar. I don't remember what I just said, but here's our answer. Sorry, someone came in to talk to me and I had to pause my lecture video, and so now I don't remember what's the last thing I said. But anywho, this is a very basic molarity problem that we will work, okay? Just like in algebra, like if we were solving for the density formula, D equals M over V, you can solve the problem for M. You can also use algebra and solve the problem for V, okay? That's still what I would consider a basic concept, still what I would consider a basic use of the molarity formula, okay? So let's work another problem. This problem here is a lot like the other one. It's giving us grams of solute and milliliters of solution. So again, we would just convert and solve moles over liters, okay? I want to take a little bit of time and show you one where you have to use some concepts, some higher chemistry concepts, like so. Let me move that up. Calculate the number of moles of chlorine ions in 1.75 liters of a 1 times 10 to the negative third molar zinc chloride solution. Okay, so using our formula, M equals moles over liters. If I want to solve for moles, I use algebra to where I have moles equals liters times molarity. Okay, because within that molarity formula, I'm going to have liters times moles over liters. Okay, so hopefully this will help you see why our units cancel the way that they do and we're left with moles. Okay, so let's take the information that we're given. I have for my number of moles, and remember, I'm still working with the compound, so moles of ZnCl2 is going to be equal to 1.75 liters of solution multiplied by 1 times 10 to the negative third moles per liter. Okay, so again, anytime you see the letter M, moles over liters. Okay, so 1.75 times 1 times 10 to the negative third is going to give us moles equals 0.00175 moles of ZnCl2. Okay, so just like we started seeing in the last chapter, when I have a compound, 1 mole of ZnCl2, it's made of 2 moles of chlorine and it's made of 1 mole of zinc. Okay, this problem wants moles of chlorine, so I'm going to take my 0.00175 moles of ZnCl2 and I'm going to go from moles of the whole compound to just moles of chlorine. So in 1 mole of ZnCl2, I have 2 moles of chlorine. So 2 times 0.00175 gives us 0.0035 moles of chlorine atoms. Okay, so this is another very common theme to get used to. So we used, oh, sorry, I'm having a hard time scrolling up on my picture. We used our basic definition of molarity to solve for moles. Then I took the numbers that were given to me in the problem, and then I started trying to analyze my values or analyze what I have based off of the concept of the mole. Okay, if I know the chemical formula, I can write a mole-to-mole ratio with our atoms that we're interested in. Okay. Here's one more molarity problem where we're just using the definition to help us. So what volume of blood serum contains 1 milligram of NaCl? Okay, so there's a lot of different ways that you can solve this problem. That's what I want you guys to see. I just naturally try to use dimensional analysis any way that I can, just because I like it. That's the way that my brain works. But you guys can also still just use our formula here. So if I'm solving for liters, multiply by liters on both sides. And so to get volume by itself, I'm going to dissolve moles over molarity. Okay? You can solve this problem using that exact method. I want to show you how I would do it with dimensional analysis. So I would start with 1 milligram of NaCl, milligram of NaCl to grams of NaCl, grams of NaCl to moles of NaCl, because that's our magic unit. And because I know my molarity, that means that I know there are 0.14 moles of NaCl in 1 liter of solution. So I can go from moles of NaCl to liters. This problem didn't ask us for any specific unit of volume, so I'm going to take it to liters and I'm just going to see what it looks like. If I think that it'll look prettier with milliliters, then I'll change it. Okay, so 1 gram is 1,000 milligrams. 1 mole is 58.45 grams. 1 liter is 0.14 moles as determined from the problem. And so that gives me, with sig figs, 1.2 times 10 to the negative 4 liters of solution. And so that's right, but you could also divide it by 1,000 and use 1.2 milliliters as an answer too. So it really just depends on what the problem's asking for. But I wanted to show you how you can still use algebra like we taught you in Chem 1, but it's also probably a good move to evolve as a chemistry student to be able to start seeing molarity. So I think it's a good move to be able to start seeing molarity as a conversion factor. There's more to come with molarity and dilution, and it's just a second. All right, the last part of this section is going to actually start talking about how to make solutions, like what you would use in a lab. So I'm still in section 4.3. To make a solution, you're going to use a volumetric flask. So you have a couple of different sizes in your lab bench, but in the volumetric flask, you always weigh out the solute first. So you use your molarity formula, M equals moles over liters. Typically, when you're making a solution, you already know what molarity you're making, and you also know how much, so you know the volume, as seen by if this is a 100 milliliter graduate or volumetric flask, you know that you're measuring out 0.1 liters. And so what you would solve for is how many grams that you need to actually weigh out on the lab bench, okay? Or measure out with your balance. So you have solute dissolved in the volumetric flask. One of the big key steps is make sure that you dissolve all solid before filling. Okay, that is crucial. Whenever I'm watching you guys do this lab, you never do this step. So please make sure that you dissolve all of your solids. So you swirl, swirl, swirl. There's no solid left, and then you dilute to the line. Okay, make sure that your meniscus is above the line, right? Just like you would if you were looking at a graduated cylinder. Okay, so making solutions is super fun. It's probably one of my favorite things that we did in analytical and instrumentation chem. It's a very basic process when you're in a lab or you're doing kind of any little procedure. So it's very, I think it's fun. You guys always like parafilm, which I give you guys to cover the top instead of Sometimes we have these lids, but most of the time we don't, so just using the little parafilm will work. So I think up next I have a problem. To analyze the alcohol content of a certain wine, a chemist needs a liter of 2 molar solution. How much must be weighed out to make the solution? So pause the video and work it on your own, and then unpause me and see if you got it right. Okay, so after you do the molarity calculation to solve for your moles, we know that we are measuring out potassium dichromate. And so after, we're going to know that we're going to measure out 58.8 grams. And that's what's going to be dissolved in a 1 liter volumetric flask. So you would measure it out on your balance. And then this is going to be a 1 liter volumetric flask. You'll put all of your solid into this using distilled water. You'll dissolve it with distilled water, dissolve, 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 and then fill up to the line with your meniscus. Okay, let me make another slide. So, making dilutions. We talked about dilutions in Chem 1, but we never actually got to do one. Some of you did, but most classes didn't. So the formula that you need to make a dilution is MV equals MV, where molarity is obviously moles over liters, and you can use any volume of solution, okay? When you make a dilution in the lab, you're going to be using exclusively a volumetric flask is the most precise way to do it, but you also will be using pipettes. And notice that these are not just the plastic pipettes. They're actually glass. They're calibrated so that we know exactly how many milliliters they're holding. You'll use pipette bulbs. I think that when you guys do your lab, it has you doing the dilution in graduated cylinders. So that works, but it's not a super precise way to do dilutions. But again, it'll work. So obviously, the MV equals MV formula is one that you have to memorize along with your molarity formula. And I have a problem here. So what volume of 16 molar sulfuric acid must be used to prepare 1.5 liters of 0.10 molar H2SO4 solution? So pause the video, see if you can solve it, and then unpause me and see how you did. Okay, so hopefully after working the problem, this is the answer you arrive at. So it gave us that we want to use the stock solution of 16 molarity. We didn't want to know how much of it we need, and so then we solve for X. The problem didn't ask for any certain unit, but you can convert this to milliliters just because leading zeros aren't necessarily something that we use all the time in chemistry. All right, let's see if we have another one. Okay, this problem is what I would call a marathon type problem. It takes a little bit of everything that we've done so far and wraps it all up into one question. So it says, all right, so the problem says, a solution is prepared by dissolving 10.8 grams of ammonium sulfate. So that's NH4, 2SO4, in enough water to make 100 milliliters of solution, of stock solution. Then we take 10 milliliters of the sample of the stock solution and add it to 60 milliliters of water. Calculate the concentration of ammonia ions. So I want to know the concentration of ammonia, and I want to know the concentration of sulfate. So that's moles per liters. Moles per liters. So first place that we're going to start is from trying to figure out what the concentration of the stock solution is. All right, so it tells us that we took 10.8 grams NH4, 2SO4, gram to mole. So my molar mass, when you divide that out, you get 0.0817 moles. And then the problem told me that we had 100 milliliters of the stock solution, so that's 0.1 liters. Off my sig figs. And so that tells me that the concentration of my stock solution is 0.817 molar. So that's what I started with. Now, in the next process, I took my 0.817 molar stock solution, and I specifically took 10 milliliters of it, and then I diluted it and made a new solution. Okay, so notice I took 10 milliliters of stock and I added it to 50 milliliters of water. So that gives me 60 total milliliters for my new solution. Okay, so I want to know what the concentration is for my 60 milliliter solution. Divide by 60. Notice that milliliters cancel, and that leaves us with 0.136 molar. Okay, so I just drew that big one. We know that our new diluted solution is 0.136 molar NH4 to SO4. And we want to specifically calculate how many, or the concentration of ammonium ions and the concentration of sulfate ions. Okay, so we need to take a relationship like we did in the last chapter, chapter 3. So I know that in order to make 1 mole of NH4 to SO4, I need 2 ammonium ions, right? We can see that in the chemical formula. In order to make 1 mole of NH4 to SO4, I need 1 sulfate ion. Okay, and these are both moles. So, taking my definition, because I know molarity, I know that that means I have 0.136 moles of ammonium sulfate per 1 liter of solution. Okay, if I want moles per liter for both of my ions, all I'm going to have to do is use our mole to mole ratio. So, for instance, moles of ammonia. So that's going to give me 2 over 1. So look what happens with our units. I'll use a different color to emphasize it. My moles of NH4 cancels with the moles of NH4, and we are left with moles of ammonia per liter of solution. And that's exactly what we want. So 0.136 times 2 is going to give us an answer of 0.272 molar ammonium. Okay, so because ammonium sulfate only has 1 mole of sulfate, I have the same concentration of sulfate ions as I do the solution. Okay, so here's our final answers. I have 0.72 molar NH4 ions and 0.136 molar SO4 ions. So again, we started with our molarity formula, which is what we did at the beginning of the lecture. Then we use the dilution formula to come up with what our diluted solution is. And then the last thing, because chemistry loves molar relationships, is we had to dissect what our chemical formula is telling us. To make 1 full compound, I need 2 ammonium ions, I need 1 sulfate ion. And so that helped us calculate the concentration that we have in solution. So Please become comfortable with the fact that if I had something that's 0.5 molar, that means that I have 0.5 moles in 1 liter of solution. Okay, this is a very common relationship that we're going to use over and over and over again.